The night sky holds a question that has haunted thinkers for millennia. Where does the cosmos actually end? We are about to explore one of astronomy's deepest mysteries, the shape of the universe's edge, and the startling possibility that no such boundary exists at all. By the end, you will see the entire cosmos and your place within it in an entirely new light. We will venture from the explosive birth of the Big Bang to the dizzying concept of a multiverse, uncovering how the very fabric of reality defies a simple border. So much of what we think we know about limits is about to be challenged. What does it truly mean for something to have an edge? We think we know what an edge is. It is the sharp rim of a dinner plate, the precipice of a canyon where the ground simply stops. But when we lift our gaze to the heavens, that everyday idea collapses. The cosmic frontier is not a place you could touch or fall from. Instead, it involves the farthest reaches of everything we could ever possibly see, the very limits of space, time, and matter itself. Is the edge the final point of the universe's expansion, a frontier of ongoing creation, or is it an absolute boundary, a literal nothingness beyond which existence ceases? Ancient cultures grappled with this by envisioning physical domes or great walls holding up the sky, a comforting, tangible border to the unknown. Modern cosmology, however, presents us with a far more dizzying proposition, a universe that might be finite in size yet have no edge at all. This is not a contradiction, but a clue that we are thinking about the problem in the wrong way. To truly grasp what could shape a cosmic edge, we must first look at the forces that define reality from its very first moments. That primordial moment of creation, the Big Bang, was not an explosion in space but an explosion of space. Picture the entire cosmos, every galaxy and every star, compressed into a single point of near-infinite density and heat. Then space itself began to stretch and expand, a process that has continued for roughly 13.8 billion years. This initial expansion did more than just create room for everything to exist. It imprinted the cosmos with its fundamental structure. The slight variations in density from that first instant became the seeds for everything we see today. Over immense spans of time, gravity pulled on those slightly denser regions, drawing matter together to form the vast cosmic web of galaxies and galaxy clusters we observe. We can even see a faint echo of that initial hot state today, a cosmic microwave background radiation that fills the entire sky. This afterglow is the oldest light in the universe, a baby picture of the cosmos when it was just a newborn. So when we ask where the edge is, the Big Bang offers a profound clue. It represents a beginning in time, not a location in space that we can visit. There is no center to the expansion, and no outer wall where the explosion's debris field ends. Every point in the universe was once that initial hot, dense state. This means the edge we are searching for is not a place you could travel to, but a horizon in time, a limit to how far back we can see. This leads us directly to the next great cosmic frontier, the boundary of our own vision, the observable universe. This observable sphere, stretching 46.5 billion light-years in every direction, is the ultimate expression of our cosmic isolation. We are at the very center of this vast but finite volume, not because we are special, but because we are the observers. Every point in the cosmos has its own unique observable universe, its own personal cosmic horizon. The light from the most distant galaxies we can see has traveled for nearly the entire age of the cosmos to reach our telescopes. This light is a message from the deep past, showing us these galaxies not as they are today, but as they were in their infancy. This creates a profound illusion, a celestial zoo where every exhibit is a fossil. the edge of this sphere is not a physical wall you could crash into. It is a horizon in time, a limit set by the finite speed of light and the relentless expansion of space itself. As the universe ages, this horizon slowly shifts. Light from regions that were once too distant finally has time to reach us, bringing new galaxies into view. Yet, this expansion is also working against us. The universe is not just growing, its expansion is accelerating, driven by a mysterious force we call dark energy. Because of this acceleration, there are galaxies whose light is only now beginning its journey toward us. They are so far away that the space between us is stretching faster than light can cross it. Their light will never arrive. They are forever receding beyond our event horizon, their stories lost to us for all time. This reveals a startling truth: the edge of our knowledge is not fixed. It is a moving boundary defined by a race between the speed of light and the stretching of space. So when we speak of an edge to the universe, we must first ask, an edge for whom? Your edge and my edge are the same, but an observer in a distant galaxy would have a completely different cosmic horizon. This forces us to confront a deeper question: does a true, absolute edge to everything exist, independent of any observer? Or is the universe in its totality something far stranger, a cosmos that needs no edge at all? This rapid expansion solves a major cosmic puzzle known as the horizon problem. When we look at the cosmic microwave background in opposite directions, we see regions that should have never been in contact, separated by distances light could not have crossed in the age of the universe. Yet they are almost exactly the same temperature. How is this possible? Inflation provides the answer. By stretching a tiny, uniform patch of the primordial cosmos to an unimaginable size, it ensured that the entire observable universe was once a single, connected neighborhood. This explains the remarkable uniformity we see today. The theory also explains why the cosmos is so flat. Just as inflating a balloon makes its surface appear flatter and flatter from any single point of view, the inflationary stretching of space smoothed the universe into the geometrically flat cosmos we measure. This leads to a staggering implication about the true scale of everything. The patch that inflated to become our entire observable universe, a sphere 46.5 billion light-years across, was just one infinitesimal speck in a much vaster region undergoing the same explosive growth. What we call our entire cosmos, with its billions of galaxies, may be just one island in an archipelago of universes, a single bubble in a cosmic foam that is vastly larger, perhaps even infinite. The edge we have been searching for begins to vanish, not into a wall, but into a boundless expanse of reality we can never see. This expansive view of a cosmos without borders is the gateway to an even more profound idea: the multiverse. Our universe could be a single bubble in a foaming sea of cosmic domains. This is the Multiverse Hypothesis, a framework where the very idea of an edge transforms from an absolute end into a mere border crossing. Within this grander meta-universe, our entire cosmos, with all its galaxies and stars, might be just one island in an archipelago of reality. Each of these other universes could have formed with a different set of physical constants, a unique cosmic recipe where the strength of gravity or the mass of an electron might be slightly altered. In some, matter might never have clumped into atoms, while in others, stars could have burned out in an instant. The edge of our universe, then, would not be a cliff into nothingness but a shoreline. It would mark a transitional zone where the laws of physics as we know them give way to an entirely different kind of reality. One compelling version of this comes from the theory of cosmic inflation. We already saw how a brief period of hyper-expansion could have stretched a tiny patch of space into our vast observable universe. But what if that inflationary process never truly stopped? What if it is ongoing in regions far beyond our horizon, continuously giving birth to new cosmic bubbles? In this inflationary multiverse, space is a constantly churning cauldron where new universes nucleate like bubbles in a boiling pot, each one a self-contained realm with its own properties, forever separated from us by the ever-expanding fabric of the meta-universe. String theory adds another layer to this tapestry with its concept of the landscape, a vast mathematical terrain of possible physical laws. Our universe would simply occupy one stable valley in this landscape, while countless other valleys represent entirely different realities. From this perspective, the search for an edge becomes a search for a door. It challenges the very foundation of a singular, definitive boundary by placing our home within an infinitely richer context. If our cosmos is but one thread in this boundless tapestry, then its shape must be defined not by a wall, but by its intrinsic geometry. The true nature of the cosmic edge may depend entirely on the overall curve of space-time itself. Einstein's theory of gravity gives us a cosmic map, but its directions are unlike any we have ever seen. It presents three possible shapes for the universe itself, and the choice among them determines whether an edge can exist at all. The first possibility is a flat universe. In this geometry, parallel lines would never meet, and the angles of a triangle always add up to 180 degrees, just as we learned in school. If the universe is truly flat, then it is almost certainly infinite, stretching on forever in all directions without any boundary or edge. The second shape is a closed universe, which we can picture as the three-dimensional surface of a four-dimensional sphere. This cosmos would be finite in size, yet you could travel in a straight line forever and never hit a wall, eventually looping back to your starting point. It is a universe with no edges, much like the surface of the Earth has no precipice you can fall from. The third and final possibility is an open universe, a shape with a negative curvature, like an infinite saddle. Here, space would bend away from itself and parallel lines would diverge. This, too, would be infinite and without an edge. So how do we choose between these cosmic blueprints? The answer is written in the oldest light we can see. By studying the subtle patterns in the cosmic microwave background, the afterglow of the Big Bang, scientists have taken the universe's temperature. They look for tiny ripples in this ancient light, imprints of the earliest sound waves that traveled through the primordial cosmos. The size of these ripples acts as a cosmic ruler. In a flat universe, the most prominent ripples we observe should appear at a very specific angular scale on the sky. And this is exactly what our most powerful telescopes, like the Planck satellite, have found. The measurements align almost perfectly with a flat geometry. This single observation carries a breathtaking implication. The universe we inhabit appears to be flat, which strongly suggests it is also infinite. An infinite cosmos has no edges because it has no boundaries to define them. The very concept of an edge dissolves into an endless expanse. This geometric insight does more than just redraw our maps of reality. It sets the stage for the universe's final act, a destiny written not in the stars but in the very shape of space and time. The geometry of space is not just a static blueprint. It is a script for the universe's final act. Its ultimate destiny hinges on a cosmic tug of war between two invisible forces, the relentless pull of gravity and the mysterious push of dark energy. Our cosmic fate, and with it the very idea of a final boundary, rests on which of these forces ultimately wins. One possible ending is the Big Crunch. In this scenario, the collective gravity of all the matter in the cosmos eventually halts and reverses the expansion. galaxies would begin rushing back toward each other, space itself contracting like a deflating balloon. Temperatures would soar as everything is compressed back toward a single, ultra-hot point, a mirror of the Big Bang in reverse. This would create the most definitive edge imaginable, a final moment in time where the universe ceases to exist as we know it, collapsing into a singularity. A second, and currently more likely, ending is known as the heat death. Here, dark energy maintains its dominance, driving an eternal and accelerating expansion. Galaxies will be pulled so far apart that the night sky will grow utterly black, each island universe isolated in a void. Stars will burn out, matter will decay, and the cosmos will approach a state of perfect equilibrium, a cold, dark, and uniform stillness. In this eternal expansion, there is no spatial edge, only a temporal one, a slow fading of all structure and energy into an endless, diluted quiet. The most dramatic finale is the Big Rip. This occurs if dark energy grows stronger over time. Billions of years from now, its repulsive force would first tear apart galaxy clusters, then individual galaxies. As the acceleration intensifies, it would rip stars from their systems and planets from their stars. In the final moments, atoms themselves would be shredded, and the very fabric of space-time would be torn asunder. This would create a different kind of edge, a frontier of dissolution that sweeps across the cosmos, not a wall in space, but a wave of catastrophic incoherence. Current data from observing distant supernova and the cosmic microwave background points toward a universe dominated by dark energy, making the heat death the most probable of these three fates. This suggests a cosmos that never truly ends, but simply fades into a vast, cold, and silent equilibrium. The edge becomes not a place you could find, but a state of being, a final, eternal condition. Each of these destinies reframes our search for an edge from a question of location to one of time and process. The true boundary of reality may not be a line on a map, but the final chapter of its story, a chapter being written by the enigmatic force of dark energy. This accelerating expansion is perhaps the most profound discovery in modern cosmology, fundamentally rewriting our cosmic forecast. The force driving this acceleration, dark energy, acts as a kind of anti-gravity, pushing the very fabric of space apart at an ever-increasing rate. Imagine a vast, stretching canvas on which every galaxy is a painted dot. As the canvas grows, the dots move farther apart, not because they are traveling, but because the space between them is itself expanding. Dark energy is the hand that pulls that canvas taut, and its grip is only tightening. This relentless push means that distant galaxies are not merely receding, they are accelerating away from us. There will come a time for each of them when the space between us is stretching so fast that the light they emit, no matter how powerful, can never hope to cross the growing divide. They will vanish one by one from our future sky, not by exploding or dying, but by simply slipping beyond an unreachable horizon. This creates a profoundly personal edge, a boundary to our knowledge defined not by a physical wall, but by the ultimate speed limit of the universe, the speed of light, being outpaced by the expansion of space itself. Scientists grapple with the nature of this mysterious force through two main ideas. The first is the cosmological constant, a concept originally introduced by Einstein. This suggests that dark energy is an inherent property of the vacuum of space itself, a constant energy density that does not dilute as the universe expands. Think of empty space not as truly empty, but as a seething sea of quantum activity that exerts a gentle, persistent pressure. The second idea is called quintessence, a dynamic field that changes over time and space like a fifth fundamental force. Whether it is a constant or a shifting field, the dominance of dark energy has a dramatic effect on the large-scale structure of the cosmos. It acts to smooth out the universe, fighting against gravity's tendency to pull matter together into clusters and superclusters. Over eons, it will lead to a more and more isolated existence for any remaining islands of matter. This paints a picture where any notion of a static, fixed edge is an illusion. The boundary of our observable universe is not a permanent frontier, but a shrinking island of visibility in an ever-widening sea. The very space that connects us to the rest of the cosmos is actively carrying it away. Yet, while dark energy dictates the expansion of space, another hidden component governs the growth of cosmic structure, an invisible scaffold that holds the universe together. But while dark energy stretches the cosmic canvas, an unseen sculptor is simultaneously at work, shaping its grandest structures. This sculptor is dark matter, a substance that refuses to interact with light, making it completely invisible to our telescopes. We cannot see it, touch it, or even detect it directly, yet we know it is there by the unmistakable grip of its gravity. It is the hidden architecture of the cosmos, a framework upon which the glittering cities of galaxies are built. Without this invisible scaffolding, the universe as we know it would simply fly apart. The stars you see on a clear night are like lights on the surface of a vast, dark ocean, hinting at the immense, unseen currents flowing deep beneath. Dark matter makes up roughly 27% of the entire mass-energy content of the universe, a dominant presence that guides the formation of everything we can see. Its gravitational pull acts as a cosmic glue, gathering the sparse clouds of hydrogen gas in the early universe into the first protogalaxies. Over billions of years, these seeds grew into the majestic spirals and giant ellipticals that fill the sky today. But dark matter's influence extends far beyond individual galaxies. It weaves the largest pattern in existence, the cosmic web. Picture an unimaginably vast spiderweb, with galaxies clustered like dewdrops at the intersections of silken threads. These threads are filaments of dark matter stretching across billions of light years. They connect immense clusters of galaxies, while also walling off vast, empty regions known as cosmic voids. These voids are the true deserts of space, enormous bubbles of near-nothingness that can span hundreds of millions of light years. So, where does one of these voids end and the web begin? There is no sharp line, no physical barrier. Instead, the edge is defined by a gradual increase in the gravitational tug from the surrounding dark matter filaments. It is a frontier of density, a place where the pull of hidden matter gently guides gas and galaxies, shepherding them toward the bustling nodes of the web. This interplay between the dark matter scaffold and the luminous matter it holds creates the rich texture of the cosmos. It offers a completely different perspective on cosmic edges. They are not walls of nothingness but transitional zones, shores between oceans of emptiness and continents of clustered matter. This gravitational landscape, shaped by the invisible hand of dark matter, ultimately determines the very topology of the universe, the fundamental shape of all that exists. This hidden architecture of dark matter defines more than just cosmic geography. It shapes the very topology of space. Topology is the mathematical study of shape, but not in the way we normally think of it. A topologist considers a coffee mug and a donut to be identical because one can be smoothly deformed into the other without cutting or tearing. What matters are the fundamental properties like the number of holes. This perspective transforms our search for an edge. The universe could be finite without having a single boundary if its global shape is wrapped in on itself. The most straightforward topology is a simply connected space where any loop you draw can be shrunk down to a point. But what if the cosmos is not so simple? Imagine a universe with the shape of a three-dimensional torus, like a giant cosmic donut. In such a space, if you could point a powerful telescope in one direction and look far enough, you might see the back of your own head. The light from your galaxy would have traveled all the way around the universe, returning to its starting point. There would be no edge to find, only an endless loop. This is not just a mathematical curiosity. It leaves a potential fingerprint on the oldest light we can observe. Scientists meticulously study the cosmic microwave background for matching patterns, circles in the sky where the temperature fluctuations are identical. Finding such pairs would be strong evidence that space is folded back on itself, that the cosmos is smaller than it appears and multiply connected. While no definitive proof has been found, certain anomalous features in the data, like large-scale patterns that seem improbably aligned, keep the possibility alive. The profound implication is that an edge might be a complete illusion, a limitation of our local perspective rather than a feature of reality. We assume that space must end somewhere because everything in our daily experience does. But the universe is under no obligation to conform to that intuition. This mathematical approach dissolves the idea of a boundary into a question of connections. If you can travel forever and simply return to your beginning, then the very concept of an edge loses all meaning. We are then faced with a cosmos that is self-contained, a complete and seamless whole. This shifts the search from a physical frontier to a deeper understanding of the fabric of existence itself, leading us to a final, humbling contemplation of what a truly boundless reality implies for our place within it. Our minds are not built to grasp the infinite. We instinctively carve the world into manageable pieces with clear beginnings and ends. This is the very dilemma that philosophers like Immanuel Kant wrestled with centuries ago. He proposed that space and time are not discoveries we make about the world, but fundamental frameworks of our own perception, the very lenses through which we are forced to experience reality. To us, an edge is a necessity, a way to make sense of our surroundings. Yet modern cosmology presents us with a universe that may defy this deep-seated need for a boundary. The scientific concept of a cosmic horizon, the limit of what we can ever observe, is not just a physical frontier. It is an epistemological one, a boundary of knowledge itself. It asks a profound question: is the edge we are searching for out there in the cosmos, or is it an artifact of our own limited perspective, a cage of our own cognition? This blend of physics and philosophy dissolves the line between the map and the territory. We are left to wonder if the ultimate shape of the universe is not a geometric form, but a reflection of the mind attempting to comprehend it. This journey beyond conventional boundaries leads us to one of the most radical ideas in all of physics, a principle that suggests the entire three-dimensional cosmos, with all its galaxies and stars, might be a projection from a two-dimensional surface. The very fabric of reality could be a cosmic hologram. This radical idea finds its roots in the most extreme environments the universe has to offer: black holes. When a star collapses into a black hole, it forms an event horizon, a point of no return from which not even light can escape. Physicists once faced a deep puzzle. If you throw an object packed with information into a black hole, what happens to that information when the black hole eventually evaporates? Is it lost forever, violating a fundamental law of quantum physics? The holographic principle emerged as a breathtaking solution. It proposes that all the information about every object that falls into the black hole is not lost within its depths, but is instead perfectly encoded on the two-dimensional surface of its event horizon. The three-dimensional volume of the black hole is, in a sense, projected from the information written on its two-dimensional boundary. Now, take this staggering concept and apply it to the entire cosmos. Our universe has its own horizon, the limit of what we can ever observe. The holographic principle dares to suggest that our rich, three-dimensional reality, with its galaxies, planets, and every experience you have ever had, might be a magnificent projection from a vast, distant, two-dimensional surface at that cosmic horizon. The edge of the observable universe would no longer be a simple frontier of sight, but the cosmic equivalent of a film projector's screen, the source from which all of reality is rendered. This transforms the very definition of an edge from a wall of nothingness into the ultimate hard drive, storing the code for everything we perceive. The solidity of the world around you, the depth of space, even the flow of time itself, could all be emergent properties, illusions generated from a vast, flat, informational canvas we can never directly see. This blurs the fundamental line between what is inside and what is outside. If the universe is a hologram, then the distinction between here and the horizon is an illusion. The entire cosmos is an interconnected whole, with its essence written at its perceived boundary. The search for an edge leads us not to a place, but to a profound question about the nature of existence itself, inviting us to consider that space and time may not be the fundamental stage of reality, but a language written for us to experience. Einstein's revolutionary insight was that space and time are not a static stage, but a dynamic fabric, a single entity we call space-time. This cosmic fabric can be stretched, warped, and curved by the presence of mass and energy, like a trampoline sagging under a heavy weight. This curvature is what we experience as gravity, but if this fabric can be bent, can it also be torn? Does the cosmic tapestry have a frayed edge where the weaving simply stops? The mathematics of general relativity describes this fabric as inherently smooth and continuous. In most regions of the universe, from the empty voids between galaxies to the gentle gravitational well of a star, the equations paint a picture of a seamless continuum. There are no coordinates where the fabric abruptly ends, no mathematical stitch lines marking a boundary. An edge, in this context, would be a place where the smooth geometry of space-time terminates, where the rules of physics as we know them cease to apply. The most compelling candidates for such an edge are singularities. These are points of infinite density and curvature, like the very center of a black hole or the moment of the Big Bang itself. Here, the equations of general relativity break down, yielding nonsensical answers of infinity. For decades, physicists viewed these singularities as the ultimate endpoints, the true and final edges of reality. Yet, most scientists now believe that singularities are not physical realities, but rather signals that our current theory is incomplete. They are mathematical artifacts, placeholders for a deeper theory of quantum gravity that would seamlessly take over where Einstein's equations fail. They mark a frontier of our understanding, not necessarily a wall in the cosmos. This picture becomes even more intriguing when we consider structures like wormholes. Often depicted in science fiction as tunnels or shortcuts through space, a wormhole, if it could exist, would be a topological feature of the space-time fabric itself, a bridge connecting two distant regions. If you were to approach one end of a wormhole, would you encounter an edge? Not in the traditional sense. You would simply be passing through a doorway in the continuum, a feature woven into the very geometry of reality. The existence of such structures would profoundly complicate the idea of a simple, singular boundary for the entire universe. Instead of a single edge, the cosmos might be filled with countless portals and intricate folds, a labyrinthine fabric with no definable perimeter. When we trace the smooth, continuous nature of space-time back through cosmic history, we are led inexorably to its origin. The initial conditions of the universe become the ultimate subject of our inquiry. If the fabric has no edge now, did it have one at the very beginning? the initial singularity presents us with a profound paradox. It is the ultimate cosmic starting line, a moment when all of space and time were compressed into an infinitely dense and hot point. Yet, infinities in physics are often a sign that our theories have reached their breaking point. The singularity is not so much an edge of the universe as it is the edge of our understanding, a place where the smooth predictions of general relativity dissolve into nonsense. What if this apparent beginning was not a true beginning at all, but merely a transition? Some of the most compelling ideas in theoretical physics propose exactly that. They suggest our universe was born not from nothing, but from the death of a previous cosmic era. In the framework of loop quantum cosmology, for instance, the cosmos avoids the catastrophic singularity through a process called the Big Bounce. Imagine the previous universe not ending in a fiery crunch, but contracting to a point of immense yet finite density. At that moment, the repulsive force of quantum gravity would become so powerful that it would reverse the collapse, triggering a new expansion and birthing the universe we inhabit today. In this cyclical view, the cosmos is eternal, breathing in and out in vast cosmic cycles, each one giving rise to the next. There is no starting edge because the timeline of existence forms an endless, unbroken loop. This transforms the Big Bang from a moment of creation into a moment of rebirth. Other models, like conformal cyclic cosmology, propose a different kind of eternity. In this vision, our universe will expand and cool forever, until all matter eventually decays and particles lose all sense of scale. In this featureless, high-entropy state, the end of time effectively becomes a new beginning, seamlessly connecting to the next cosmic cycle's hot, dense singularity. The boundary between the end of one eon and the start of the next simply vanishes. These theories collectively shift our focus from a single, definitive starting point to a continuous, unending process. The search for an initial condition becomes a search for a phase transition, a cosmic turning of the page rather than the opening of the first chapter. This invites us to consider cosmologies where the universe has always existed, forever transforming, with no first moment and therefore no first edge to find. The Big Bang is not the only story the universe could have told. For much of the 20th century, it faced a formidable challenger, the steady-state theory. This elegant idea proposed a cosmos with no beginning and no end, an eternal, unchanging universe that had always existed and would always remain. To maintain this perfect state as space expanded, the theory suggested that new matter was continuously and slowly created in the voids between galaxies, just enough to keep the overall density constant over time. In this vision, the universe had no edge because it was fundamentally the same everywhere and everyone, a boundless, infinite reality with no moment of creation. While compelling, this model could not withstand the discovery of the cosmic microwave background, the definitive afterglow of a hot, dense past. The steady-state universe faded from favor, but its philosophical challenge remains, asking us why we assume a beginning is necessary at all. This line of thinking finds a modern echo in cyclic models of the cosmos. Imagine the universe not as a single explosive event, but as a timeless, rhythmic breathing. In one such model, known as the ekpyrotic universe, our three-dimensional reality is a membrane or brain existing in a higher dimensional space. A collision between our brain and a neighboring one could provide the immense, concentrated energy we observe as the Big Bang, not as a beginning from nothing, but as a transformative collision in an eternal cosmic dance. This collision would be followed by an expansion phase, which would eventually give way to a new approach and another collision, a cycle repeating forever. In this endless rhythm, each cosmic cycle is finite in duration, but the overarching timeline has no start and no finish. There is no edge to the process itself, only periodic rebirth. The boundary of one universe becomes the seed of the next, a cosmic phoenix rising again and again from its own ashes. These alternatives stand in stark contrast to the prevailing lambda-CDM model, our current standard model of cosmology. Lambda-CDM incorporates the Big Bang, dark energy, and dark matter into a coherent, evidence-based framework. It tells a story with a definite beginning and a forecasted, fading end. Yet, even within this dominant model, the nature of an edge remains elusive. The universe may be finite or infinite, but its observable portion is all we will ever know. The existence of these competing cosmologies is not a sign of failure, but a testament to the richness of scientific inquiry. They demonstrate that a cosmic edge is not a mandatory feature of reality, but a concept that depends entirely on the underlying physical laws we assume. Our search for a boundary is therefore also a search for the correct cosmic recipe. This profound uncertainty forces us to confront the ultimate limit on our knowledge, a barrier imposed not by theory, but by the very nature of light and time. The very laws of physics that allow us to see the stars also conspire to hide the greater cosmos from our view. This creates not one, but two distinct cosmic horizons, each defining a different kind of limit to our perception. The first is the particle horizon, a frontier marking the farthest distance from which light has had time to reach us since the dawn of the universe. It is the ultimate time capsule, a sphere containing every scrap of information we could possibly gather about the past. Beyond it lies not emptiness, but regions whose light is still traveling toward us, a future inheritance of cosmic knowledge. The second, more permanent boundary is the event horizon. This is not a physical wall, but a consequence of the universe's accelerating expansion. Galaxies too distant are being carried away by the stretching of space itself at a speed greater than light can overcome. Their light dispatched toward us today will simply never arrive, destined to swim eternally against a current that flows too fast. They are not vanishing from a place, but receding from any possibility of contact. These horizons define the accessible universe, a stage illuminated for our observation, while the vast backstage remains shrouded in permanent darkness. Even our most ambitious future telescopes, peering deeper into space and further back in time, will eventually bump up against this fundamental curtain. They can push our particle horizon slightly outward, but they can never pierce the event horizon. This starkly reveals that the edge we often speak of is not a feature of the cosmos, but a limit of our own circumstance. It is a horizon of knowledge, a final page in a book whose later chapters are written in ink we cannot see. This profound isolation, however, sets the stage for a deep cosmological puzzle. If we are so separated from distant realms, how can we explain the universe's remarkable uniformity from one end to the other? This deep, underlying uniformity is the bedrock of modern cosmology. It is captured in a single, powerful idea known as the Cosmological Principle. This principle makes two profound claims about the universe when we zoom out to its grandest scales. First, it is homogeneous. This means the cosmos has a fairly even distribution of matter, like a well-mixed batter where any large scoop will contain roughly the same number of chocolate chips. Second, it is isotropic. This signifies that the universe looks the same in every direction you look, with no special axis or preferred orientation. There is no cosmic north, no center stage, and no unique edge. From the perspective of any galaxy in any corner of the cosmos, the view would be fundamentally the same. This is a radical declaration of cosmic democracy, asserting that our position is in no way special or central. The evidence for this sweeping uniformity is written across the sky. Massive galaxy surveys, which map the positions of millions of galaxies, reveal a vast cosmic web that stretches for billions of light years. While this web has dense clusters and vast empty voids, these features are distributed evenly when you look at scales larger than a few 100 million light years. The real clincher, however, comes from the cosmic microwave background. This ancient light shows only the tiniest of temperature fluctuations, variations of just 1 part in 100,000. The primordial universe was stunningly smooth. This afterglow appears almost perfectly uniform from every point in the sky, a direct observation that the early cosmos adhered to this principle of sameness. This has a staggering implication for the idea of an edge. If the universe is truly the same everywhere and in every direction, then there cannot be a unique boundary, a singular place where everything stops. A true edge would be a glaring exception, a place that is fundamentally different from all others, violating the very principle that governs the large-scale cosmos. Instead, the structure we see here simply repeats, presumably forever. This points toward a cosmos that is boundless, an endless tapestry where every location is the center of its own observable universe, and no location holds the title of the final frontier. This geometric flatness is more than just a fact about angles. It is a profound statement about the totality of everything. If the universe is truly flat, as our best measurements indicate, then it is almost certainly infinite. There is no boundary, no wall, no final galaxy because the cosmic fabric simply continues forever. Infinity is not just a very big number, it is a complete redefinition of reality. It means that every possible configuration of matter within the bounds of physical law must eventually repeat. Somewhere, in the vastness beyond our horizon, there is an identical copy of our Milky Way galaxy. There is another Earth with another you, living a life almost indistinguishable from your own, and there are versions where a single choice diverged, creating infinite variations. This is not science fiction, but a direct mathematical consequence of an infinite, flat universe. The concept becomes even more bizarre when we consider the role of random chance over infinite time and space. In such a cosmos, the spontaneous formation of a self-aware brain from a random fluctuation of particles, a so-called Boltzmann brain, becomes not just possible but statistically inevitable. These disembodied observers would briefly flicker into existence, convinced of a reality that does not structurally exist, only to dissolve back into the chaos. The unsettling question then arises, how can we be sure we are not such a random fluctuation ourselves? This paradox challenges our most basic assumptions about consciousness and reality, suggesting that in an eternal, infinite universe, the most unlikely events are not just possible, they are guaranteed to happen an infinite number of times. While this seems to defy all logic, it aligns perfectly with the mathematical framework of our leading cosmological models. The universe does not need to make intuitive sense to us, it only needs to obey its own physical laws. To find a possible resolution to these dizzying implications, we must look back to the very beginning, to the quantum realm where the rules of common sense break down and a different kind of logic takes over. The solid ground of our cosmic reality may rest upon a foundation of pure chance. At the tiniest scales imaginable, the vacuum of space is not empty or still. It is a seething, bubbling sea of potential, where pairs of particles and their antiparticles spontaneously wink into existence, only to annihilate each other a moment later. These are quantum fluctuations, brief loans of energy from the universe itself, and they are happening everywhere, all the time. In the first fleeting instance after the Big Bang, when the entire cosmos was compressed into an unimaginably small and energetic state, these tiny ripples in the quantum fabric were stretched to monumental proportions by the violent expansion of space itself. The slight over-densities and under-densities created by these quantum jitters became the gravitational seeds for everything we see today. Every galaxy cluster, every swirling nebula, and every solitary star owes its existence to microscopic quantum vibrations amplified across the cosmos. This idea pushes the origin of structure back from the domain of classical physics into the bizarre and counterintuitive world of quantum mechanics. It suggests that the entire cosmic web, with its vast filaments and immense voids, was woven from the threads of quantum uncertainty. If the universe itself began as a quantum event, then the very concept of a definitive starting point becomes blurred. Perhaps our cosmos did not emerge from a singular point of infinite density, but from a transition, a quantum leap within a broader, pre-existing reality. In this view, what we call the Big Bang could have been the moment our local region of space underwent a phase transition, like a bubble of steam forming in a pot of boiling water. Our entire universe, in all its immensity, would be just one such bubble in a vast, eternal quantum foam, a meta-stable vacuum where different pockets of space can have entirely different properties and physical laws. Each bubble universe would be a localized phenomenon, born from a quantum fluctuation and expanding into its own reality. From inside our bubble, we can only perceive the reality defined by our own laws of physics. The edge of our universe, then, would not be a wall of nothingness, but the boundary of our cosmic bubble, a domain wall where our local physical laws give way to an entirely different and likely unimaginable set of rules. We could never cross this boundary, for to do so would mean the dissolution of the very atoms that make us who we are. This quantum perspective elegantly merges with the earlier idea of an inflationary multiverse. The same quantum fields that drove the hyper-expansion of our early universe could be eternally active in the wider metastable vacuum, continuously giving birth to new cosmic bubbles, each with its own unique history and destiny. In such a reality, the search for an absolute edge is once again transformed. There is no single boundary for the whole of existence, only the relative boundaries of countless individual universes, each one a self-contained reality within an infinite, frothing quantum sea. This leads us to a final, humbling thought, that the ultimate nature of the cosmos may be beyond geometry, residing instead in the fundamental probabilities and possibilities of quantum creation itself. Our entire cosmos could be a single bubble adrift in a sea of countless others. This is the powerful imagery of eternal inflation, where the fabric of reality is a frothing, ever-expanding foam. Each bubble in this cosmic foam is a universe in its own right, nucleating from the unstable energy of the meta-universe and inflating to an immense size, just as our own patch did. Within each of these isolated realms, the fundamental constants of nature could be set to different values. The strength of gravity, the mass of an electron, even the number of spatial dimensions might be unique to each bubble, creating a staggering diversity of realities. Some might be stillborn, collapsing instantly, while others could be vast, sterile voids where matter never coalesced. Our universe, with its just right conditions for life, would be one fortunate ticket in an infinite cosmic lottery. The boundary of our universe, then, is not a cliff into nothingness, but the domain wall of our bubble. This is not a place you could touch. It is a transitional zone where the physics we know and rely upon would gradually or abruptly shift into an entirely different set of laws. The very forces that hold your atoms together would cease to function, meaning crossing such a frontier would be an act of dissolution. While these bubble walls lie forever beyond our observable horizon, their existence might not be completely hidden from us. Scientists have theorized that if another cosmic bubble had collided with ours in the distant past, the immense energy of that impact could have left a faint, circular imprint on the cosmic microwave background, a bruise on the oldest light in the sky. Telescopes have searched for these anomalous patterns, a potential smudged fingerprint from a neighboring reality. No definitive evidence has been found, but the search itself transforms the multiverse from a philosophical idea into a testable scientific hypothesis. This vision of a bubbling metacosmos completely redefines the meaning of an edge. There is no single, absolute limit to all of existence, only the relative boundaries of countless individual universes, each one a self-contained reality. Within this eternal churn, the very structure of space is continuously reborn, leading us to ponder the ultimate measure of cosmic change and decay, the relentless growth of entropy. This relentless increase in disorder is written into the fundamental laws of physics. The second law of thermodynamics states that the total entropy, a measure of randomness or chaos in a closed system, can never decrease. It is the reason a shattered glass does not spontaneously reassemble itself, and why heat always flows from a warmer object to a colder one. This gives us the arrow of time, the irreversible direction from past to future that defines our experience of reality. The entire cosmic story, from the Big Bang's hot, ordered beginning to the cold, dispersed future, is a grand expression of this single law. The early universe was a state of incredibly low entropy, a highly ordered and dense configuration. Ever since that initial moment, the cosmos has been evolving toward states of higher and higher disorder, like a clock slowly but inexorably winding down. This thermodynamic journey shapes everything from the life cycle of a star to the formation of a galaxy. It is the engine driving the universe toward its most probable final state. In the scenario of a heat death, this process reaches its ultimate conclusion. After trillions upon trillions of years, when the last stars have burned out and all matter has potentially decayed into radiation, the universe will approach a state of maximum entropy. In this final equilibrium, energy is uniformly distributed throughout space. There are no hot spots or cold spots, no concentrations of matter, no structures of any kind. The temperature everywhere would be just a fraction of a degree above absolute zero. In this profound and featureless uniform state, the very concept of an edge dissolves completely. How could you locate a boundary in a cosmos that is perfectly identical in every direction, a sea of sameness with no landmarks to define here from there? A place where nothing ever happens and no change is possible has no need for frontiers. This thermodynamic perspective offers a different kind of answer to our search for a boundary. It suggests that the ultimate edge is not a place but a condition. It is a state of such perfect disorder that all distinction, all form, and all information are lost. The universe does not hit a wall, it simply fades into a final, silent equilibrium. This slow march toward uniformity is already visible in the vast, empty regions that stretch between the galaxies, the cosmic voids where the pull of entropy is already winning. These cosmic voids are the true deserts of the universe, stretching for hundreds of millions of light years. They are regions of profound emptiness, where galaxies are so scarce that you could traverse one for a lifetime and see only blackness. Yet, despite their staggering emptiness, these voids are not the edges we have been searching for. They are not walls of nothingness marking the end of the cosmos. Instead, they are an integral part of its architecture, the deep valleys in the rolling hills of the cosmic web. Their existence tells a story of gravitational evolution. In the early universe, matter was distributed almost but not perfectly evenly. Over billions of years, gravity acted as a cosmic sculptor, pulling matter from the broad, flat planes into the dense clusters and filaments. The voids are what was left behind, the regions that lost the gravitational tug of war. As matter drained away toward the growing web, these areas became ever more empty, expanding in volume as the space within them continued to stretch. Think of a sponge. The holes are not breaks in the sponge's structure, they are essential to its form. In the same way, these vast empty regions define the shape of the universe just as much as the glittering galaxy clusters do. They are not a boundary but a phase of the cosmic landscape, a testament to the pulling power of gravity and the initial conditions of reality. This interconnected nature, where emptiness and fullness define each other, points toward a cosmos that is a single, self-contained system. There are no abrupt endings, only gradual transitions from one part of the grand design to another. The universe seems to be a complete and seamless whole, a closed loop of cause and effect where every region, no matter how empty, is woven into the same cosmic fabric. Physics often treats the entire cosmos as the ultimate closed system, a self-contained reality with no outside environment. Within this framework, the very idea of an edge becomes a logical contradiction. An edge implies a separation between an inside and an outside, a distinction between what is part of the universe and what is not. But if the universe is defined as the sum total of all matter, energy, space, and time, then there is literally nothing else. There is no external vantage point from which to look back and see its boundary. This perspective is deeply woven into the conservation laws that govern reality, such as the conservation of energy. The total amount of energy in the universe remains constant. It can neither be created nor destroyed, only transformed. For this law to hold true, the system must be closed. There can be no external source adding energy, nor any external sink draining it away. The cosmos operates with a finite balance sheet, a complete and self-sufficient economy of existence. This system's view reveals that our persistent search for a boundary is a projection of our own experience. We live on a planet with a surface, in rooms with walls, and we instinctively apply this model of containment to the cosmos itself. We assume reality must be inside of something, but what if the universe is not inside anything at all? What if it simply is a complete whole that requires no external container? The concept of an edge is then exposed not as a physical necessity, but as a human construct, a cognitive tool that fails when applied to the totality of everything. This profound shift in thinking, from looking for a wall to understanding a complete system, was only possible after a revolution in our understanding of the fundamental stage upon which reality plays out. That revolution was Einstein's theory of relativity, which forever intertwined the concepts of space and time. Einstein shattered the notion of a universal stage where events play out the same for everyone. His theories revealed that the measurements we hold as absolute, like the length of an object or the timing of an event, are not fixed. They depend entirely on your state of motion and the strength of the local gravitational field. Two observers moving at different speeds or standing in different gravitational environments will fundamentally disagree on what they see. This principle of relativity extends to the very concept of a cosmic edge, transforming it from a fixed frontier into a fluid and personal perception. Imagine a traveler moving at a significant fraction of the speed of light. For this high-speed observer, the distances to faraway galaxies would contract dramatically due to an effect known as length contraction. The edge of their observable universe, the point from which light has just had time to reach them, would not be in the same place as it is for us, sitting still relative to the cosmic background. They would measure a different cosmic horizon. their edge and our edge would be in different locations, and both would be equally correct within their own frames of reference. There is no single, privileged viewpoint from which to declare the definitive boundary of reality. This ambiguity deepens when we consider the unity of space and time. Relativity fused these two separate concepts into a single, flexible fabric, space-time. In this four-dimensional continuum, an edge cannot simply be a location in space. It would have to be a boundary in space-time, a surface that separates events we can experience from those we cannot. But since the passage of time itself is relative, slowing down near massive objects or for fast-moving observers, this surface loses its absolute meaning. What one observer sees as a simultaneous moment defining a spatial boundary, another will see as a succession of events stretched across time. The universe does not present a single, solid edge for all to see. Instead, it offers a spectrum of horizons, each one valid for a specific observer at a specific moment. This profound shift in perspective prepares the ground for an even more radical departure from classical intuition. The smooth, continuous fabric of space-time described by Einstein must ultimately grapple with the fuzzy, probabilistic world of the quantum. The universe, according to Einstein, is a smooth, continuous fabric, but the quantum world tells a different story altogether. At the tiniest scales, reality is a fuzzy, probabilistic dance of particles popping in and out of existence. This creates a fundamental conflict at the heart of physics. General relativity beautifully describes the cosmic stage of space and time, while quantum mechanics governs the actors upon it. But in the most extreme environments, like the center of a black hole or the first moment of the Big Bang, these two rulebooks give contradictory and nonsensical answers. To resolve this, we need a theory of quantum gravity, a single framework that can describe the universe where the very large and the very small become one. This pursuit takes us to the ultimate limit of smallness, the Planck scale. At this unimaginable size, 100 million trillion times smaller than a proton, the smooth fabric of space and time itself is thought to break down. It is here that the concept of an edge may finally vanish, not into a wall, but into a fundamental graininess. How can space have a boundary if it is not infinitely divisible, but is instead made of discrete, indivisible units? This is the promise of theories like loop quantum gravity. It proposes that space is not a continuum, but is woven from tiny, finite loops. Picture the fabric of reality not as a smooth sheet, but as an incredibly intricate tapestry of individual threads. These loops connect to form a network, a spin foam, that gives rise to the three-dimensional space we experience. In this view, there are no singularities, no points of infinite density. The Big Bang was not a true beginning, but a rebound from a previous cosmic phase, a big bounce. The question of what came before the Big Bang transforms, because there was no before in a singular sense, only a continuous transformation of the quantum geometry of space. This eliminates the need for an initial edge entirely. String theory offers another path to unification, suggesting that the fundamental entities are not point particles, but incredibly tiny, vibrating strings. The different vibrations of these strings correspond to different particles and forces. To make the mathematics work, string theory requires extra dimensions of space, curled up into shapes so small we never perceive them. In some versions of the theory, our universe is a three-dimensional membrane or brain floating in a higher dimensional bulk. A collision between brains could have ignited our Big Bang. In this picture, the edge of our universe is not a boundary in nothingness, but a real surface in a higher dimensional space. We are trapped within our brain, unable to perceive the greater dimensions, making our cosmic horizon a function of our dimensional confinement rather than an absolute end. Both of these approaches and others like them share a common goal: to eliminate the infinities that plague our current theories. By quantizing space itself, they replace the nonsensical singularity with a smallest possible scale. There is no infinite curvature because there is no space for it to exist within. The geometry of the cosmos becomes a tapestry of finite stitches. This suggests that at the most fundamental level, the universe is a seamless, interconnected whole. The sharp divides we imagine, the edges between something and nothing, may be illusions born of our coarse-grained perception. We see a smooth pond, but a closer look reveals the individual water molecules. As we push our understanding to these radical frontiers, we are guided by a language that seems to be written into the cosmos itself, the universal language of mathematics. Our intuitive discomfort with infinity finds its sharpest challenge in pure mathematics. While our minds struggle with the concept of endlessness, mathematicians have developed precise languages to describe and even categorize different sizes of infinity. One of the most famous thought experiments is Hilbert's Hotel, a conceptual establishment with an infinite number of rooms, all of which are occupied. If a new guest arrives, the manager simply asks every current guest to move to the next highest room number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on forever. This frees up room 1 for the new arrival, demonstrating that infinity plus 1 is still infinity. The hotel can, in fact, accommodate an infinite number of new guests through a similar shuffling of occupants. This paradox highlights how an infinite set behaves in ways that defy our everyday arithmetic, yet it remains logically consistent within its own rules. Cosmologists use this same logical framework to model a universe that is unbounded and eternal. In such a cosmos, the question of where to put one more galaxy is not a problem because an infinite space can always accommodate more. The mathematician Georg Cantor took this further, proving that some infinities are actually larger than others. For instance, the infinite set of all whole numbers is smaller than the infinite set of all decimals between 0 and 1. This hierarchy of infinities provides a toolkit for physicists who describe a cosmos that may be infinite in extent, in duration, or even in the number of parallel realities. These are not merely philosophical musings, they are the working components of our most successful cosmological models. The equations of general relativity that describe the expanding universe, and the quantum field theories that govern the behavior of particles, both seamlessly incorporate infinite concepts. When we say the universe is flat and therefore likely infinite, we are making a mathematical statement that has real, physical consequences. This application transforms infinity from a baffling abstraction into a practical, predictive tool. It allows us to comfortably describe a reality that has no need for an edge, a seamless whole that simply is. This leads to a humbling reflection on our own perception. Our brains evolved to navigate a world of finite objects and clear boundaries, a world where resources are limited and paths have ends. This deep-seated intuition is ill-equipped to handle the true scale of a cosmos without limits. We are like creatures who have only ever known a small, quiet pond, suddenly trying to comprehend the existence of an endless ocean. The feeling of vertigo that comes from contemplating the infinite is not a failure of understanding, but a sign that we are brushing against the very limits of the human mind. Mathematics becomes our raft on this ocean, a constructed vessel that allows us to explore realities for which our senses never prepared us. Our own minds may be the source of this deep need for a cosmic fence. From the moment we open our eyes as infants, we learn to navigate the world by identifying objects, by seeing where one thing ends and another begins. This cup is separate from the table, the tree from the sky, our own body from the air around it. Our survival has depended on this fundamental skill of boundary recognition, a cognitive tool honed over millions of years of evolution. We are pattern-seeking creatures, and an edge is the most basic pattern of all. So when we lift our gaze to the heavens, we instinctively project this same framework onto the cosmos, searching for the final tree, the ultimate cup, the last line where the universe itself simply stops. It is a deeply ingrained habit of thought, one that has shaped our stories and our science for millennia. Ancient cultures did not have telescopes, but they possessed powerful imaginations, and they universally filled the void with comforting structures. Many envisioned a great dome or a solid firmament arching overhead, a physical lid on the world. Others told of a cosmic egg from which all of existence was hatched, providing a natural, tangible shell. Some myths describe the sky as being held up by immense pillars or giant beings, creating a vast but enclosed room. These were not naive fantasies. They were brilliant psychological solutions to the terrifying prospect of an endless, unbounded reality. They gave the cosmos a shape the human mind could comprehend and accept. Even our modern scientific horizons, like the observable universe or the event horizon of a black hole, serve a similar purpose. They are not necessarily physical walls, but they are conceptual boundaries, edges to our knowledge that make the infinite feel manageable. They are the cognitive containers we build to hold a universe that might be fundamentally uncontainable. Recognizing this deep-seated bias is the first step toward a more mature cosmic perspective. It allows us to question whether the feeling of vertigo we get from an infinite universe is a clue about the cosmos or a confession about the limits of our own perception. Perhaps the universe is not strange for having no edge, we are strange for needing one. This psychological journey, from ancient myths to modern mental models, forces us to consider the responsibility that comes with looking into the abyss. As we push these boundaries of understanding, we must also ask what our place is in a cosmos that might truly have no end. A universe without edges profoundly redefines our understanding of home. If there is no center and no periphery, then every point is, in a sense, the center of everything. This cosmic democracy dismantles the ancient idea of a privileged vantage point, challenging narratives that place humanity at the physical heart of creation. Our planet becomes not a singular stage for a special drama, but one world among a potential infinity of others, a single note in a symphony of unimaginable scale. This perspective can feel deeply unsettling, even humbling, as if our individual stories are being diluted into cosmic insignificance. Yet, this very humility may be the key to a more mature and meaningful worldview. By releasing the need to be the central characters in the universe, we open ourselves to a different role, that of the conscious witness. We are the part of the cosmos that has awakened, able to look back upon itself with wonder and ask these profound questions. This shifts the source of our purpose from our location to our capacity for understanding, from a place of privilege to a moment of awareness. Religious and philosophical traditions across the world have long contemplated the infinite and the eternal, often using these concepts to point toward a reality beyond ordinary comprehension. The scientific revelation of a boundless cosmos does not necessarily contradict these spiritual insights, but rather provides a new, evidence-based vocabulary for them. It invites a sense of awe that is grounded in observation, a reverence for the intricate laws that allow such complexity to emerge from simplicity. This interconnected view of reality, where every particle is linked through the fabric of space-time, encourages an ethical stance of unity. The same physical laws that govern the most distant quasars also operate within our own bodies. The atoms in our hands were forged in the hearts of long-dead stars, making us literal children of the cosmos. Recognizing this deep kinship can foster a greater sense of responsibility, not just for our local environment, but for the fragile spark of consciousness that has flickered into being here. The practical benefit of studying these cosmic limits, or their absence, is precisely this expansion of perspective. It trains the mind to hold vast ideas, to find comfort in the unknown, and to appreciate our fleeting moment of sentience within an endless unfolding story. The true edge we face may not be in the stars, but in our own ability to embrace a universe that needs no walls. The search for a cosmic edge has gifted us more than just philosophical insight. It has reshaped the technology we use every single day. Our ability to pinpoint a location on Earth with astonishing accuracy is a direct result of this celestial inquiry. The Global Positioning System, a network of satellites orbiting our planet, would be useless without the corrections derived from Einstein's theory of general relativity. These satellites experience time slightly differently than we do on the surface, their clocks ticking faster in the weaker gravity of space. If engineers did not account for this subtle warping of time, GPS coordinates would drift by several miles each day, rendering turn-by-turn navigation impossible. This is not an abstract concept. It is a daily demonstration that the laws governing the vast cosmos are intimately woven into the fabric of our modern lives. The same drive to peer deeper into space has also revolutionized how we see our own world. The need to process the faint light from distant galaxies pushed the development of more sensitive digital image sensors, technology that now resides in every smartphone camera. The algorithms created to clean up the static in radio telescope signals have been adapted to improve medical imaging, allowing doctors to see clearer scans of the human body. Even the challenge of managing the immense flood of data from observatories has driven progress in computing and machine learning, creating tools that now help us predict weather patterns and understand complex financial markets. These are the tangible rewards for daring to ask the biggest questions. The quest to understand the shape of everything has, in turn, given us new tools to improve life on our own small planet. As this technological legacy continues to grow, it fuels an even more ambitious future for discovery, one that may ultimately reveal the final, fundamental nature of the cosmos itself. The relentless quest to understand the cosmos now builds its next generation of eyes and ears. Instruments of unprecedented power are being readied to stare deeper into the void than ever before, hunting for the faintest whispers from the dawn of time. The James Webb Space Telescope, with its golden mirrors tuned to the infrared, acts as a cosmic time machine. It peers through cosmic dust to see the very first stars and galaxies igniting, testing our models of inflation by examining the universe in its fragile infancy. By studying these ancient structures, we can measure how the initial seeds of the cosmic web were sown, looking for subtle imprints that could confirm or challenge the entire inflationary paradigm. Meanwhile, on the ground, the square-kilometer array will not see the sky but listen to it. This colossal network of radio antennas will map the distribution of neutral hydrogen across billions of light years, charting the cosmic web in 3 dimensions with breathtaking precision. It will trace the influence of dark energy across cosmic history, watching how the expansion rate has changed over eons and putting our forecasts for the universe's ultimate fate to the test. These are not merely bigger telescopes, they are entirely new senses for humanity, designed to probe the fundamental laws that might govern a multiverse. They will scour the cosmic microwave background for any anomalous patterns, any strange correlations or cold spots that could be the bruised fingerprint of a collision with another cosmic bubble in the vast inflationary foam. The data they gather will not give us a simple answer, but it will provide the first hard evidence to weigh our most speculative ideas against reality. Will the universe appear perfectly consistent with a single, smooth, and infinite expanse, or will the data reveal subtle cracks in that picture, hints of a larger architecture beyond our current horizon? This forward-looking view grounds our philosophical wonder in the gritty reality of engineering and data. The mysteries of cosmic edges and boundaries are no longer purely theoretical. They are becoming measurable, empirical questions. The journey to map the ultimate frontier of reality is just beginning, and its greatest revelations likely lie in the signals we have not yet learned how to see. For all our profound discoveries, the cosmos still holds its deepest cards close. The true nature of dark energy remains one of the greatest enigmas in physics. Is it a constant force woven into the vacuum of space, or is it a dynamic field that could change over time, perhaps even weakening or strengthening to alter the universe's ultimate fate? The answer dictates whether our cosmos will fade into a cold, quiet equilibrium or face a more dramatic dissolution. This mystery is inseparable from the puzzle of the Big Bang's initial conditions. Our equations trace the universe's history back to a singularity, a point where the laws of physics as we know them break down entirely. What, if anything, came before that moment? Was it a true beginning from nothing, or a transition from a previous cosmic phase, a bounce or a collision in a far grander reality? We simply do not know what set the entire cosmic story in motion. These unresolved questions breathe continuous life into the most speculative ideas, like the multiverse. Without direct evidence, the concept of countless other universes remains a powerful but unproven framework, a mathematical possibility that elegantly explains the bizarre fine-tuning of our own cosmic home. The fact that these fundamental mysteries persist is not a failure of science, but a testament to its vitality. It means the story of the cosmos is still being written, with every new telescope and every novel calculation offering a chance to rewrite what we think we know about the edges of reality. This evolving landscape of cosmology ensures that our map of the universe is a living document, forever open to revision and awe-inspiring discovery. Our journey has revealed a cosmos where edges seem to dissolve upon closer inspection. The observable universe gives us a personal horizon defined by light and time, not a solid wall. The theory of inflation suggests our entire cosmic domain is just one bubble in a boundless, frothing meta-universe. The holographic principle radically reimagines our three-dimensional reality as a projection from a distant two-dimensional surface. And quantum origins hint that everything we see emerged from probabilistic vibrations, not a definitive starting point. Each of these frameworks, from the relativistic to the quantum, converges on a similar profound insight. The boundaries we instinctively search for are not absolute features of reality, but are relative to an observer, or are illusions born from the limits of our perception. They are horizons of knowledge rather than walls of existence. This synthesis points overwhelmingly toward a universe that is seamless, self-contained, and likely infinite in nature. The very laws of physics, from the conservation of energy to the geometry of space-time, describe a complete system that requires no external container and thus no ultimate edge. This collective evidence does not make the cosmos feel smaller, but infinitely richer and more interconnected. It prepares us for a final, humbling contemplation of what this boundless reality means for our own fleeting, yet deeply meaningful, place within the endless whole. This idea of a boundless reality is far more than a theoretical curiosity. It has the power to reshape how we approach the world, transforming our sense of place and possibility. When we internalize that the fundamental architecture of existence may have no hard borders, it encourages us to challenge the perceived limits in our own lives and disciplines. In science, this expansive perspective is the engine of innovation. Researchers are not confined by the idea of a final frontier. Instead, they are driven by the understanding that every answer uncovers deeper questions, that knowledge is an endless horizon. This mindset fuels the search for unified theories and pushes engineers to develop technologies capable of seeing further and thinking smarter. The drive to map a cosmos without edges has already given us everything from precise GPS to breakthroughs in medical imaging, proving that the pursuit of cosmic questions yields profoundly earthly rewards. This philosophy naturally extends into education, fostering a curriculum built on curiosity rather than rote memorization. It teaches the next generation to embrace the unknown, to see the universe not as a closed book of facts, but as an infinite story in which they are active participants. This shift from learning what is known to exploring what might be possible cultivates the critical thinkers and creative problem solvers our future demands. On a societal level, the concept of a borderless cosmos reinforces our shared planetary citizenship. If the universe itself draws no definitive lines, then the divisions we create between nations and cultures are human constructs. Viewing our planet from this cosmic vantage point, as a fragile, blue marble adrift in an immense ocean of space, makes our conflict seem small and our collective stewardship essential. It fosters an environmental ethic rooted in interconnectedness, a recognition that the same laws of physics that govern distant galaxies also sustain the ecosystem outside our door. Ultimately, contemplating a universe without edges is a humbling yet liberating exercise. It invites us to replace a mindset of scarcity and limitation with one of abundance and potential. The greatest discoveries often lie just beyond the boundaries of what we currently believe is possible, waiting for a mind bold enough to question the very idea of a wall. So, let these ideas settle for a moment. If you were to embark on a journey in a perfectly straight line, traveling for year after year, for billions upon billions of years, what do you honestly believe you would eventually encounter? A wall, a shimmering barrier, or would you simply find more galaxies, more cosmic voids, more of the same grand, repeating tapestry? Now turn that question inward. How does the possibility of a cosmos without any true boundary, a reality that simply continues, reshape your own sense of place within it? Does it feel lonely or does it feel liberating? These are not questions with easy answers, but they are essential to the human experience of the universe. We invite you to share your reflections in the comments below. What does a borderless reality evoke in you? This conversation is a vital part of the discovery, a way to make these vast concepts personal and to see them through the unique lens of your own perspective. Our journey ends not at a wall, but with a profound shift in perspective. We have ventured from the explosive birth of our cosmos to the dizzying possibility of a multiverse, and at every turn, the idea of a simple cosmic edge has dissolved. The universe reveals itself not as a contained object, but as an unbound, interconnected whole, a seamless fabric where horizons are personal and boundaries are illusions. This quest to map the ultimate frontier is far more than a scientific endeavor. It is a reflection of a deep human desire to explore and to comprehend the vast unknown that surrounds us. It is the same spark of curiosity that has guided explorers, artists, and thinkers throughout history, so I encourage you to carry this perspective with you. Keep looking up at the night sky with a sense of wonder and keep questioning the nature of reality. For in the cosmos, every mystery we solve does not close a door, but reveals a new and even more magnificent horizon. Thank you for joining this exploration. If you enjoyed contemplating these deep space mysteries, consider subscribing for more journeys to the edges of our understanding.